Sir, can we start, sir?
Yes, madam. We can go ahead.
Okay, thank you, sir.
Yeah, welcome.
Life is a journey with problems to solve and lessons to learn, but most of all, experiences to enjoy. A very good morning, everyone. On behalf of the students and staff, PG and Research Department of Chemistry, I express great pleasure in having you all today to witness and experience this national webinar. Let us begin this beautiful day by invoking the presence of Mother Tamil by Tamil Thai Varthu.
சீராரும் மதனமென திகழ்வரத கண்டனிதில் எக்கணமும் அதில் சிறந்த திராவிடனன் திருநாடும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற
Leadership is the capacity to translate vision into reality. One such leader is our Madam Principal, Dr. S. Kodai, who has always remained as a pillar of support and guidance in translating our visions into reality. I extend a hearty welcome to you, ma'am. I'm delighted in welcoming Mrs. M. Vijaya, Head in Charge, PG and Research Department of Chemistry, who has always motivated us in all our endeavors. Beauty is no accomplishment on its own. It's what you do with it. This is very true, not just in nature or life, but also in this emerging branch of science called the supramolecular chemistry that is rapidly expanding at the frontiers of molecular science. It is indeed a great pleasure and privilege to have with us today Dr. R. Nandakumar, Professor, Department of Applied Chemistry, Karanya Institute of Science and Technology, Coimbatore, as our resource person to enthrall us with the beauty of supramolecular chemistry and the impact it is creating in the world of science. A very warm welcome to you, sir. I would also like to welcome the staff and students of PG and Research Department of Chemistry, Ethraj College for Women. I also welcome and appreciate the presence and participation of students from other colleges. Thank you.
Thank you, Preeta. Now, I would like to call upon Dr. Gokulavani, Assistant Professor, PG and Research Department of Chemistry, to introduce our chief guest.
Most respected Madam Principal and Secretary, Ethraj College for Women. Respected Head in Charge of the Department of Chemistry, respected Professor R. Nandakumar, the resource person of the webinar, dear colleagues from our institution and from other institutions, dear student participants and research scholars, I welcome you all. Last academic year, we had a new course introduction in the syllabi for advanced learners in the postgraduate level, namely Supramolecular chemistry. In connection with this, we were seeking for an expert in the field for a webinar, and we had an opportunity to invite Professor Nandakumar, who has a wide knowledge and expertise in the specified field. I'm privileged, and it is my bound duty to introduce him today in this webinar. Professor Nandakumar is a professor, Department of Applied Chemistry, Karunya Institute of Technology and Sciences. Sir obtained his undergraduation, post-graduation, MPhil, and his doctorate from Bhadyar University, Coimbatore. His research expertise are fluorescent chemosensors, supramolecular chemistry, chirality, bioorganic and medicinal chemistry, forensic chemistry, and applications. He has a wide teaching experience of 11 years and a rich experience in research for a whopping 24 years. To mention a few of his research experience are, he served as a research professor in Professor Mook Kim Research Group at the Department of Chemistry and Division of Nanosciences, Eva Women's University, Seoul, South Korea. He was a postdoc research fellow in the same laboratory for a period of 3 years. He also served as a postdoc research scientist in Professor Kim Moon Kim Research Group, Center for Supramolecular Sciences, Pohang, University of Science and Technology. He holds professional membership from Korean Chemical Society, Animal Chemical Society, the American Biographical Institute, and also a member of the International Association of Engineers. Professor has published 135 research papers in the international and 15 national journals. He has presented more than 150 research papers in national and international conferences and symposiums, and has 2 book chapters also to his publication credit. He has guided 4 PhD scholars, and 4 more are pursuing PhD under his guidance. Professor Nandakumar received many grants from both central and state funding agencies. To mention a few are 34 lakhs from DST SCRB, Government of India, New Delhi, in the year 2017, 20.3 lakhs from DST in the year 2011, both the projects successfully completed. Professor has a total of 7 patents, 2 in international level and 5 in the national level. He holds many awards and accolades like SERC Fast Track Young Scientist Award from the Government of India, Brain Korea 21 from the Government of South Korea, Best Researcher Award from Karunya University, and Bharat Gaurav Award are a few to mention. Sir, it's really a great honor to have you with us today. Over to you, sir. And thanks for accepting our invite.
Good morning to one and all. I'm Dr. Kodai, Principal, Ethraj College for Women. Welcome, sir. Welcome to our Chemistry Department, Ethraj College for Women. All the very best. Thank you very much for accepting our invitation. Thank you, sir.
Thank you, ma'am.
Thank you. Thank you, one and all, for the elaborate introduction. Thank you again. I'm really privileged to give this talk today for the Ethraj College for Women at the Department of Chemistry. I thank Dr. S. Kodai, Principal and Secretary, the convener of the meeting, and the co-convener, Mrs. M. Vijaya, the HOD in charge, Dr. Gokulavani and Ms. Uma Mageshwari, the organizing secretary for this national webinar. I thank you all for inviting me for this national webinar on supramolecular chemistry. So without wasting much time, let me directly get into the topic. So hope my slides are visible, complete.
Yes, sir.
My slides are visible?
Yes, sir.
Can I hear from anyone?
Yes, sir. Your slides are visible, sir.
Yeah,
Yes.
Thank you all. So good morning, ladies and gentlemen, in and across India or across the globe, wherever you are. So this is Professor Raju Nandakumar from the Department of Applied Chemistry, Karunya University of Science and Technology, deemed to be university. And this is our university located at the Western Ghats, the foothills of the Western Ghats and the Sirwani Hills. And this is our main building. And these are all the other buildings with the hostel here, and a very pleasant climate today, weather condition today. So today I'm going to talk about the basics of supramolecular chemistry. So we have molecules: hydrogen, nitrogen, oxygen, fluorine, so chlorine, so on. And we have synthesized many so far pharmaceutical compounds, particularly organic and inorganic metal complexes. Diclofenac, ibuprofen, they are the anti-inflammatory agents, and then chloroquine and hydroxychloroquine, so which are very famous in this pandemic situations, right? So they have helpful drugs. And the Taxol, which is a great anti-cancer activity, which has the great anti-cancer activities, which is obtained from the Pacific few trees in Japan. And this is the parahydroxyacetylide, which you call the paracetamol, which is still we are using it for many years for fever and so on things. So these are all comes under the classification of covalent bonding. That is the making and breaking of covalent bonds. So this is the synthesis of diclofenac. So we used to number the steps, how many number of steps to obtain this. Maybe there are different synthetic schemes, but these all involves the making and breaking of covalent bonds. But these guys are very difficult to synthesize. For example, if you take Taxol, it has 65 steps to obtain this final compound, many chiral centers, and many chemists are involved in it. And finally, we obtain very low yield. So it is an important drug in the treatment of cancer. So it is harvested from a scarce resource, the Pacific yew, which is there in Japan. So it is so the synthesis of these type of things is not easy. So there came we need some substitute, right? So there came this supramolecular chemistry, or we call it as the Hostges or the self-assembling process, using the supramolecular principle. So where did it come from? It is inspired from the biology, and it is built on the shoulders of traditional synthetic organic chemistry and inorganic coordination chemistry. So all it is like interdisciplinary things. So why it is deserved to be a field of study of all its own? Because we have a separate category called the supramolecular chemistry. It never belongs to an organic or inorganic or physical or analytical, but it is separately called as supramolecular. So what is that? Because it is towards the understanding and interface with the biological world and the present world of nanotechnology. And I can tell now we are in the in the area of transhuman technology, half humans and half machines. So this supramolecular chemistry plays a major role in all these things. So what is a supramolecular chemistry? In short, chemistry beyond the molecules. So the chemistry of molecular assemblies of the intermolecular bonds. It is neither the covalent nor the ionic or the coordinative bond or the metallic bond. Never. It is beyond those bonds, which we call it as the supramolecular bonds. I'll come to that later. Or we can call it in short the chemistry of non-covalent bond. So how the covalent bonded molecules, so what I've shown you before, simple drugs, because of this pandemic situation, I've given certain drugs. So these molecules, they recognize each other, they react, and they carry on each other with many applications. So these type of chemistry is called as supramolecular chemistry. So it involves investigating molecular systems in which the most important feature is the components held together by intermolecular forces. Definitely there is no covalent bonds. So atoms, by covalent bonds, we have molecules. These molecules, through the non-covalent interactions, form the supermolecules. For example, you can have the supermolecules as cyclodextrins, cucurbityrol, calixarenes. So these are all the molecular formula, and this is the graphical representation, and this is the ball and stick projection of cyclodextrin, cucurbityrol, calixarene. These are called the macrocycles. And here, these will be like host molecules, and wherein some guest molecules will be engulfed or entrapped inside these areas. I will come one by one. So these are all some other supramolecules or macrocycles: the cyclodextrin, calixarene, cyclophanes, and proteins, DNA duplics, and these days the nanoparticles, nanotubes, carbon nanotubes, micelle, vesicle, so on and so forth. There are many things. So where it finds its application? So the supramolecular chemistry finds its application in sensing. Okay, many places it is found in sensing of small molecules like metals, anions, neutral molecules, whatnot, chiral recognition. There are many things in sensing. In molecular imaging, like CT scan, MRI scan, in all those things, besides the radioisotopes, these guys are also used there in molecular imaging. In drug delivery systems, DDS, or what we call it as targeted drug delivery systems, wherein the host molecule can carry a drug to that particular place, and there it can deliver depending upon the external stimuli. And in the metal extraction, if you want to take one particular metal, and if you can have a good sensor for that metal alone, so it can be easily extracted from that ores, because it will capture only that metal. It will not capture any other thing, so that it is easy for us to take that. So its applications, and besides, it is used in many of catalysis area, and there are many developments in recent days. So the Poinis, who obtained the Nobel Prize in 1987 for their development and use of molecules with structure-specific interactions of high selectivity, in particular, which the host-guest complexes, for their contribution, wherein the host molecule recognizes and selectively binds certain guests. So this is an important contribution. This is done by Professor Donald J. Cram and Professor Jean Mary Lane, and then Professor C.J. Pedersen in the year 1987, particularly for this crown ether complexation with potassium. So that was the start of this supramolecular chemistry to boom. But you can see in the span of 30 years, okay, 3 decades, once again, the Nobel Prize winners are Jean Perret-Sauage, Professor Jean Perret-Sauage, Professor Fraser Stoddart, and Professor Bernard Feringa from France and USA and the Netherlands, for the introduction and advancements of the molecular missions based on the supramolecular principles. So in 3 decades, twice the supramolecular chemistry have got the Nobel Prizes. So we can see the importance of this supramolecular chemistry. So because they have many real world level applications. So according to the Nobel laureates, what they tell, the supramolecular chemistry is the chemistry of intermolecular bonds, covering the structures and functions of all the entities. It is formed by the association of 2 or more chemical species. Sometimes one species, it can combine with their own and form a self-assembly, or 2 or more can form host-guest chemistry, by Professor Jean Mary Lane. And Professor Oakley told it is chemistry beyond the molecule, as the chemistry of Taylor-shaped intermolecular interactions. It is the intermolecular interaction, or the chemistry of non-covalent bonds, or the chemistry beyond the molecule. You can classify the supramolecules into 3 types, mainly the molecular recognition chemistry, and the chemistry of molecules built to specific shapes, and the chemistry of molecular assembly from numerous molecules. So these are called as mechanically interlocked molecules. The examples are rhodoxine, catenane, dendrimers, fullerenes, carbon nanotubes. I'll try to touch everything in a slide, okay, because it's very vast. Supramolecular chemistry is a course actually for a semester, which goes for 5 units. So I will try to cover up everything at the surface level. The molecular recognition here, the chemistry is associated with the principle of lock and key, or it is called as the host-guest chemistry, wherein this crown ether, polyamine, cyclodextrin, calixarine all come to a part. And then the other one is the self-assembly. So that is the micelles, amphiphilic molecules, lipids, etc. So all 3 together we collectively called as the supramolecular chemistry. It exists both in the solid state and the solution state. So you can see here, these are all some of the important concepts. As I told you, molecular self-assembly. So one unit again joined with other to form a self-assembly creations like this. So this is a molecular self-assembly. Sometimes a big molecule folds itself, like we call it as nortoxane, boromiates, etc. It's called as folding. Molecular recognition, where a host molecule can recognize certain small molecules, or completely engulfed or entrapped molecules, a host-guest molecules. And then mechanically interlocked molecules, this is what I'm talking about. This is a nortoxane, this is a rhodoxane, and this is a catenane. And then dynamic covalent chemistry, how they fold each other and form different beautiful structures like racks, ladders, grids, helicates, etc. in those cases, right? So I will try to touch up everything. So generally 3 possible categories give you the supramolecular complexes. So the one is the small molecules. These small molecules, by covalent synthesis, they form the larger molecules, and these larger molecules exhibits as the host molecules. So this molecule will trap or entrap the small molecular guests. It's called the host-guest complex. So this molecule is the guest and this is the host. You can see there is an interaction between the host and guest, but definitely it is not the ionic bond or the covalent bond or the metallic bond. It is the other intermolecular forces, or we call it as the supramolecular interactions, and forms the host-guest complex. In principle, if this is the case of the host molecule, and if you take the guest molecules and if you put in, it should not be there because it is a cavity. So you have a cavity, when you put something, it falls down. But It will not happen. It will be there in the middle with some sort of interactions, which we call it as the supramolecular interactions. So this exists in both solution and solid state. So when you come to the solid state, you have larger molecules, and the smaller guest molecules go and sit in the lattice points of the molecules, the host molecules during crystallizations. So these are called as the host guest complexes in the solid state. For example, clathrates, you have zeolites, etc. So these guys trap the guest molecules. That is in the solid state. And then these small molecules, they just join by each other to form larger molecules, and by some external stimuli, that's what we call it as spontaneously they self-assemble each other to form a large aggregate, both in solution state and in the solid state. And when they form that is called the self-assembly, and at that point it can have different applications. So it is spontaneous and reversible condition depending upon the external stimuli. It may be heat, light, or any other pH conditions, etc. So it will assemble, it will disassemble. So that is the three possible categories in the supramolecular chemistry. So coming to that, we told it is not a covalent bond or ionic bond. Then what they are? So they are classified as supramolecular interactions, and they may be broadly classified as 5 types: ionic and dipolar interactions, hydrogen bonding, pi interaction, van der Waals interaction, and hydrophobic effects. The ionic interactions, that is further divided into 3: ion-ion, ion-dipole, and dipole interaction. So if you take this example, this is a tetrabutyl ammonium chloride. So wherein you can see there is an interaction between this positive nitrogen and the negative chlorine. These two interactions is called as an ion-ion interaction. But this is a supramolecule. So this is or a macrocycle, you can call it as the crown ether, crown 6. So here you can see there exists a dipole in the oxygen, between the oxygen and the cation. So you call it as the ion dipole. So this is an ion, and there exists a dipole between these two. See the ion dipole interactions. But if you take the other example, acetone, you can see here, because of this electronegative atom, there is a small negative charge and a positive charge in the carbon. So between these two, there is an interactions. It is called as the dipole-dipole interactions. In other terms, all these three combinedly, we can call it as the electrostatic interactions. So this is one type of interaction. So now you can see this is a 5 oxygen atom, and there is a cavity in the middle. But when there is a sodium atom, in principle, it should fall down, or there should be good bonded like a covalent bond or ionic bond. But nothing. It is just the interactions, the ion dipole interaction. This sodium is captured in the middle of the crown ether. Coming to the hydrogen bonding. So we have an donor acceptor model. So you should have an electronegative atom where when a hydrogen atom is attached, and nearby another electronegative atom, this oxygen and nitrogen, you have a small positive and negative charge created, and between these two there is an attraction and interactions. This is called as the hydrogen bonding interactions. For example, water, you know very well, there is because of its hydrogen bonding, its boiling point is also elevated at 100 degrees centigrade. So this is because of hydrogen bonding. So this is a donor where it donates the hydrogen, and here this guy accepts, so it's an acceptor. But here it is reverse way, the same thing. So donor and then acceptor. This is one type. Or again, it is further classified into intermolecular and intramolecular hydrogen bond. It is intramolecular between the nitro group and the hydroxy group. In orthonitrophenol, there is an interaction between these two guys, these oxygen and hydrogen. Okay, so this is another hydrogen bond. So here you can see its boiling point will be more because of this hydrogen bonding. So that is 215. But here you can see the melting point is 113 degrees centigrade, because here it is intermolecular between two molecules here when it is in the para positions. So furthermore, there are different types of hydrogen bonding, which we call it as bifurcation, trifurcation hydrogen bonding. So for want of time, I have omitted all those things, but I have just given an idea of what is hydrogen bonding. Then comes the pi-pi interactions, the third one. So this is can be divided into 4. That is the pi-pi interactions: cation pi interaction, anion pi, and the polar pi interactions. So you can see here, this is the benzene has the pi bonds inside, and this is a positive. So you have a pi and then cation, so cation pi interactions. So this is anion pi interactions, and this is polar, that is the dipole and then you have the pi interaction, dipole pi interactions, and besides you have the pi stacking. So you might have known what you mean by pi stackings. So this pi stacking, that is a sandwich model. So this is one benzene ring, this is another benzene ring. So here the electron cloud is there in the middle, but the edges, the hydrogen or the carbon has a positive charge, here will be the negative charge. So this is called as edge to face interactions, okay, between the positive and the negative charge in the middle, edge to face. And here it is centered, so it is a parallelly displaced, okay. So here what happens, the positive and the negative, and here the positive and the negative, so there is an interaction between these two, and it is called as parallelly displaced, or you can call it as face to face or the sandwich model. So this sandwich model exhibits in graphite, okay. They are held to by the face to face pi interaction. That's what we call it as the pi stackings, okay. Face to face interactions in nature, this occurs between the base pairs along the length of the double helix, which are responsible for the shape of the DNA. We call it as the double helical structures. That is because of this type of hydrogen bonding between the base pairs inside adenine, thymine, cytosine, and guanine, okay. So you may ask one question here. So this is we all know this is negative inside. So there is a positive, you can have an interaction, and this is negative here, and this may be a positive. So the dipole and pole, okay, dipole interaction may take place. But how come this is also negative and this is also negative? So how there will be an interaction? In principle, it should oppose each other. So how anion pi interaction takes place? Let's come to that later. All right, so this is what the pi interactions. Next, the van der Waals interaction. So this arises from the fluctuations of the electron distribution between two molecules. So these are the two molecules which contain the nucleus. This nucleus, when it comes towards one edge of the molecule, it will attract the electrons which surrounding this nucleus. So these electrons are attracted by this nucleus. So there exists a dipole between these two, or the electron distribution, a partial negative and partial positive charge happens. So the two instantaneous dipole attract each other, and they produce a London interactions. So this is called as the van der Waals interaction. Because of that also, the supramolecular chemistry exists. And then the hydrophobic effects. So this is the exclusion of non-polar groups. For example, inside the host molecule full of water, it is ordered. The entropic factor is not there. It is very, very, very much ordered. But when the guest molecules goes in, the water splashes out, it becomes disordered. So the displacement of these water molecules from the hydrophobic cavity is responsible for the enthalpic hydrophobic effect. This is another factor in supramolecular effects or interactions. And then the final one is the two or more organic molecules in aqueous solution. The combination creates a hole in the water. Okay, it creates a hole in the water. So two or more molecules. When you put a drop of oil inside water and you stir it, there may be many oil droplets, but after some time you can see all the oil droplets come closer together and makes one. So two organic molecules creating a hole within an aqueous phase, it gives rise to an entropic hydrophobic effect, where one hole is more stable than the two. It all tries to come together, like our amphiphilic structures. The lipid bilayers, which has the hydrophilic heads and hydrophobic tails. The heads come together and the tails will be wide enough, and when they come together, they form the micelles or the vesicles like our lipid bilayers. So these are the major 5 supramolecular interactions. Based on this, the whole of supramolecular chemistry goes around. Okay, whether it is solution state or solid state or whatever it is, self-assembly or host-guest chemistry or catenane, rhotoxane, etc., everything. So this is in order for two species to interact each other in a specific way. Professor Emil Fischer, he proposed a lock and key mechanism, and he won the Nobel Prize in 1902. So what he told the host and the guest molecule, or whatever inside, the enzyme substrate, they work like a lock and key mechanism. It depends upon the complementarity and the cooperativity between the host and the guest molecule, or the enzyme and the substrate, or you can call the receptor and the drug different names. This is recognized even before the molecular structures were very well understood. And he told it depends upon the shape and the size of the molecules, just what we see in today's nanotechnology. So this shape and size is most important in supramolecular chemistry. So there is a difference between a cricket ball, football and a basketball. If the cavity size can accommodate only football, if you put a cricket ball, it will fall down. If you put a basketball, it will not hold. Only the football can be stored inside with the help of supramolecular chemistry. That means the shape and the size is more important. That what this Professor Emil Fischer told in the lock and key mechanism. And they told it is like a lock and key, and it is so much rigid. So this is the lock and key mechanisms, which is very rigid. What he proposed is very rigid. So this is the active site of the enzyme. This is the substrate, exactly like a lock and key, because some other key will not open this lock. So likewise, the substrate should exactly fix the active site of the enzyme to have the reactions. But on the other hand, the enzymes are very flexible, and also they are conformationally dynamic, unlike the concept of this rigid lock. So that came Professor Koshland, Daniel Koshland, in 1958. He told the enzyme is more of an interactive process, whereby the active site of the enzyme changes its shape and size. And he proposed the induced fit model. Though the active site is not having the same shape and size of the substrate, it can induce this shape and size and forms an enzyme substrate complex. Similarly, what is happening from our head to toe in our body. So this enzyme can tune itself or change itself, the shape and size, such that it can accommodate the substrate, so that you can have the enzyme activities on the substrate and you can get the products. So that because of the complementary shape and the cooperativity between the enzyme and the substrate. So these are all the other names. What I told you is ligand or metal or host and guest, enzyme and substrate, or we can call it as receptor substrate, or we can call it as receptor drug or antibody antigen. All these different numerology mean different names, but everything, it comes under the host and guest, which is taking part in nature as well as in our body. How it involves the biology. So the study of non-covalent interaction is crucial to understanding many biological processes. It is from the cell structure to vision that rely on the forces of structure and information. So these biological systems in our humans and animals and plant materials are often the inspiration for the supramolecular research, what we call it as the biomimetic studies or bio-inspired studies. We just steal from the nature what is happening and we try to do synthetic coverage. For example, the DNA, which I have already told you, the double helix, because of the hydrogen bonding between the base pairs. Okay, and it forms the strong double helix model because of this hydrogen bonding. If there is no hydrogen bonding, you don't get the definite shape and size. So it's because of that. Biotin streptavidin. So this is also inside our body. The streptavidin takes the biotin binding to streptavidin. So this is the biotin streptavidin model. Because of hydrogen bonding, they have that particular host-guest complex. It is the amino acids also involved in it. And coming to the chiral drug and its binding site. For example, if you take ephedrine, which is very much used for blood pressure, lowering the blood pressure, and then pseudoephedrine, this is more effective than pseudoephedrine. So you can see when you take this ephedrine, this is a chiral moiety, and this is what the ephedrine, and this is the anionic area, this is the flat hydrophobic area, and this is the hydrogen bonding area in a three-dimensional space. So when this is there, these are all just a chiral molecule. They are all optical isomers. You can see here the OH is different here and it is different here. So you can see here when you take this hydrogen bonding, so it is focused downwards. So it can exactly trap the, what is that? The enzyme, the enzymes or the protein molecules. But in this case, the OH is the upward and there is no OH here. So no hydrogen bonding in this case, but there is hydrogen bonding in this case. So this drug is more effective when you compare to this, the receptor drug interactions. So small molecules, covalent synthesis forms the host, and there may be different guest molecules with a different shape and size. Only the shape and size which fits with the host molecule will form the supermolecule or the supramolecular chemistry. The chemistry around it is called as the supramolecular chemistry. So Professor Pedersen, when he was trying to synthesize a bis-biphenol component, this compound actually, bis-biphenol, he obtained a minor product like this. When he has taken some phenol and treated with this compound trace amount, he obtained the discovery of crown ethers in 1967. Like this is a template with the help of a sodium in the middle. So there came the evolution of this supramolecular chemistry. This is a serendipitous synthesis. We try one, we obtain the other one. And why we call it as selectivity is, so this is the host molecule. Okay, this is the host molecule. We call it as chemosensors in my research field. I'll come to that later. So there are different types of molecules, guest molecules. So we do metal ions here, different metal ions. So they have different shape and size. Only the shape and size which fits inside the cavity, you can have a host guest complex, which we call a supermolecule, and it is only because of non-covalent bonds. There is no covalent bonds or ionic bonds involved. And this guest molecule binds with the host molecule through the supramolecular interactions, wherein the shape and size of this matches with the guest molecule matches with the host molecule. All the other molecules will not fix it exactly here. So this is what we call it as selectivity in supramolecular chemistry. When you take 22 to 25 different metal ions, and if you prepare one organic molecule for that, only one metal will be captured by the host molecule. That's called selectivity. Is of no use, and that is not called as selectivity. The other one, which we call it as the sensitivity, that is how lower level, that is maybe to micro level, to nano level, even to pico level. I have seen till pico level recognition. That is called the sensitivity. So the host molecules and the drug molecule or the guest molecule, what we need, we may be very in minute quantities. That's what I'm telling about in picomolar level, or in even if possible femtomolar level. That is called the sensitivity in supramolecular chemistry. Selectivity and sensitivity. So the shape and size matters in supramolecular chemistry. All right. So everywhere, all of you will be fond of watermelons. So this is the watermelons, and this is the summer season started. So many people carve the watermelon into different shapes. That is a hobby. So like a rose or a well or something like a car. So I can see in the streets there are many watermelon selling. So its shape is oval, of course, solid. So transporting a solid, liquid, and gas differs. Okay, transporting a liquid uphill and hairpin bends is difficult, but transporting a solid is easy. But gas is very, very difficult because it expands sometimes when it is hot outside. So transporting a solid is very easy when we compare to liquid and gas. But see, this guy is in oval shape. So when you load on the truck, you cannot load this in an orderly manner. You have to throw. You can see the watermelons in a truck, how they are. They just throw, and it will be in different shapes and sizes. And we lose. For example, if we can accommodate 1,000 watermelon in a truck, but in principle, we can accommodate only 900 because many of the space is wasted. And if you pull one, others will fall down, and you have many damage pieces and everything. So this is a major problem with the size and the shape of this watermelon. There came the innovation. So they have done with the square watermelons. Okay, the Japan scientists, they have come with square watermelons. So when it is square, just like how the bricks are transported in the trucks, so they are transported in an arranged manner so that you can have the 1,000 watermelons inside the truck. And for loading up, loading down is very easy, no damages. So this is what their idea. So the shape matters here. So just the shape is changed from oval to square, you see the advantages of it. So that's what in supramolecular chemistry. So you can see here, this is the square watermelon, and this is from the watermelon yard, how they develop. They put a square box. So it grows according to the shape of the square, and then they are harvesting it, right? So not only square watermelons, so you can have whatever shape you want. No more you can teach your kids banana will be in this shape, watermelon will be in this shape, apple will be in this shape, orange will be in this shape. Those generation has gone. You whatever shape you want. This is a cucumber. You can see here star shaped, heart shaped, and apple. Have you ever imagined a square apple? So you cannot draw something in a picture for a kid and show this is what apple, this is what orange. So whatever shape you want for the convenience, you can do it. This is a pentagon orange, and you can see even like a baby in the tree. So you can tune it. See here from the tree. I think probably this is from China, like a Buddha. So no more the exact shape for one particular fruits. You can have all sorts of shapes. Not only that, you can have a football, right? You can have a football, even from the you can have a heart. So the shape and size matters in this era, particular after the advent of the nanotechnology. So based on that shape and size, the supramolecular chemistry is also involved. So for a layman explanation, I have taken all these things plus the awareness for you all people. These are all existing in this world. So this is about the cation binding. So this is the about the supramolecules, how the macrocycles are created, the host molecules. But what are all the guests? Maybe a cation, maybe anion, maybe neutral molecules, maybe many other things. So the cation complexes play an essential role in many biological studies. You know, what is the role of calcium? What is the role of iron? What is the role of zinc in our human body? Each plays a role. Whether it increases or decreases, it creates a lot many problems. It should be in normal level, particularly when you have the sodium and potassium levels. If it goes beyond the level or if it decreases, it leads to coma. So you know the ion channel process. So when you dehydrate, you go for an electrolyte. So that increases the concentration of the potassium and sodium. How do you measure it? You go to the microbiology lab and give your sample. It takes some time and then they do it. But instead, if you have a sensor for that, you can easily measure whether your potassium level is high or low. So that is what the supramolecular chemistry is useful for. So coming to this cation, how do you capture the cation? So the cyclic polyethers derived from repeating units, OCH to CH2 units, it forms stable complexes with metal ion. Synthetic reactions involving anion. So this is a particular crown ether, and this is named as 18 crown 6. This 6 is the number of oxygen atom, 1, 2, 3, 4, 5, 6. So this is the number of oxygen atom here, which we name it 6. And this 18 is this total number of the ring size. Starting from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18, and this is like a crown. So where you can put it a crown, a crown for a king or a queen. So that looks like a crown. So the name has come as crown. And this is 18 and 6 oxygen atom. The name is 18 crown 6. So here, the lone pair of electrons on oxygen atom creates the negative charge is very much concentrated inside this cavity of the molecule. So what happens? So this is what in this simulated image. So the negative charge is highly concentrated inside because of the oxygen atoms. So this crown ether can hold on to potassium cation. This can form a stable complex with potassium cation. Why not sodium? Why not lithium? The problem is the shape and size. So it can hold on to potassium, but not to lithium or sodium. This particular 18 crown 6. That's what I told you, the complementarity and cooperativity between the host molecule and the guest molecule, and the cavity, the shape and size. This is what the simulated picture. So why? A simple example for you. So this potassium fluoride, this guy is not soluble in benzene. Potassium fluoride is not soluble in benzene. But when you add a little amount of crown 6, you know that this crown 6 can capture this potassium. So it forms a complex here, host-guest complex. But what happens ultimately, this fluoride is free. So this is called as the naked anion effect. So this guy is carried into to preserve the electron neutrality, but this is not inside the cavity. Only the potassium is captured inside the cavity, but fluorine is outside. So this is highly reactive. So whenever you want to have a reaction, you can have this. If you want to substitute fluorine, any other halogen by fluorine, you can use this. You can put a little amount of 18 crown 6 inside. So what happens? The complexation of K plus by 18 crown 6 solubilizes the potassium salts in toluene. It is not soluble in K. So this is called as a naked anion. So they are very reactive. So what happens if, for an example, you can take this 1-bromo-octane if you want to substitute this bromine by fluorine, ordinarily you cannot do this reaction. But in toluene, if you put a little of 18 crown, This guy will capture all the potassium here. The fluorine is highly reactive. It will replace the bromine here. So you can get a 90% yield of conversion of one bromo-octane to one fluoro-octane. So without crown, there is absolutely no reaction. It's a simple one example I've given you. What is the use of having a receptor for cations? See here, if it is a 12 crown 4, the cavity, the shape and size exactly fixes for lithium. A 15 crown 5 for sodium, a 18 crown 6 for potassium. Similarly for rubidium, 21 crown 7, 20 because of their shape and size. But the beautiful thing here is all are spherical in shape in the case of cations, but anions, it is very, very challenging. So these are all the crown ether system. Later on, scientists thought, if we substitute this oxygen with nitrogen, what happens? They are called as azocrowns. If you substitute with sulfur, they are called as thiacrowns. And they put a bridged compound. When there is a substitute of nitrogen, they put a bridged one, and these are called as cryptons. So these all can be used as a host molecules. There are many other molecules. I've just given an idea about how the crown ether is further modified to other things. Now coming to the part of anions. So the property of anions, they come in many shapes and sizes. I have listed out here. See, fluorine, chlorine, bromine, iodine, acetylene, etc. These guys are spherical, not a problem. But if you take cyanide, hydroxide ions, these are all linear. Nitrate is trigonal planar. And phosphates, chlorates, these guys are tetrahedral. And if you take the ferric cyanides, all these guys are octahedral. So you cannot have a receptor according to this shape and size. Very difficult to synthesize receptors for anions because they are coming in many shapes and sizes. They exist in narrow pH window because if we have a receptor, it should be good at the wide range of pH. Many anions are generally coordinatively saturated, so you cannot break that saturations. So to have a receptor for anions is very difficult. But there are two types of receptors. One is charged receptors. That means you should have positively charged receptors. The other one, neutral receptors for anions. You cannot have an negatively charged receptor for anions. There will be repulsions. So like this guanidinium derivative, where you have a positive charge, so it can hold on to this carboxylate binding. Okay, these guys are guanidinium derivative. So this is triple N. So this is guanidinium, a derivative of urea and thiourea. This is a positively charged receptor, so where they can bind with a carboxylate anion. So like that, if you have a positively charged or a neutral molecule, it can capture all the anions if you want to prepare an anion receptors. So we have seen a cation receptor, anion receptor. Now we are moving to the neutral molecules. So the example is calyx 4 arranes. It just has the shape of a vase. So you can see this is a calyx arranes. Just like if you take phenol and an aldehyde, they form these type of things with an upper rim and lower rim. Inside this cavity, because of these hydroxy groups, it can capture the molecules inside. Receptor for neutral molecules based on the hydrogen bonding or van der Waals interactions, they can capture. So it takes the shape of a vase. That's what these calyx arranes are called as. This 4 represents this calyx because of this vase shape. It is called calyx. And this 4 is the number of molecules, 1, 2, 3, 4, and arranes because they are aromatic. So it is called calyx 4 arranes. If it is from the resorcinol, then they are called as resorce arranes or resorce 4 arranes or resorce 5 arranes, etc. So it resembles the FIFA World Cup, and it can even encapsulate a fullerene molecules. Okay, fullerene molecule, these calyx arranes. Neutral molecules, and these are also neutral molecules, the alpha, beta, and gamma cyclodextrin or cucurbiturial. So this cucurbiturial, so we have CB5, 6, 7, and 8. So these are also act as neutral molecule receptors. You can have, this can act as a host molecule, where inside the cavity you can have guest molecules, neutral guest molecules in particular. So this is the glycolural. 6 units of glycolural join to form CB6, and 7 units, it forms cucurbiturial 7, and 8 and 10, so on. You can have, these are all the derivatives so far it has been found out. So even 11, 12, it's a challenging task. People are doing research across the globe for that. So in a nutshell, chemistry beyond molecules. So these are all molecular precursors. They form the molecular chemistry here. by the help of covalent bonds, which can take the guest molecule inside by the help of supramolecular interaction, where those interactions between the host guest or the self-assembly of molecules, we call it as the supramolecular chemistry, the chemistry beyond molecules. So this is what, when each molecules self-assemble together. So these are all the molecules, they are all in differently oriented. So it is the phenomena where the components of the system, these are all differently oriented, but they assemble spontaneously with the help of an external stimuli like pH, heat, light, etc. So they are arranged like this. When you take the external stimuli, the self-assemble is become disassemble, and it will be like this. So the spontaneous and reversible association of molecules or ion, we call it as self-assembly to form a larger, more complex supramolecular entities. Just like when you switch on the light hits the mirror and the mirror will be opaque. So when the light hits the mirror, all the molecules which is there in the glass coated, it will assemble and it will become opaque. But put off the light, when the stimuli is taken, the molecule disassemble and the window will be transparent. One application I'm talking about, the self-assembly. Okay, and then the soap action of the micelle formation. So they all join together, they perform their action, and then they disassemble. And it is a reversible reaction too. That's the self-assembly process. Coming to the next one, mechanically interlocked supramolecules. So the mechanically interlocking means is just like two rings threaded together. Absolutely, there is no covalent bond or ionic bond. Two or more species become connected to each other, not via chemical bonds, but they are threaded. Just like if two bangles are threaded, or the rings, how they are called as mechanically interlocked supramolecules around one another. And when they are done, they have different applications. So this is what that you can see. This is a molecule and this is another molecule. Only because of intermolecular reactions, this molecule is held up in the middle. There is no covalent bond. These type of things are called as rhotoxanes. When these are called as the capping end, okay, it is capping, or the bulky molecules cap so that this molecule will not slide away. If there is no cap, it is called as pseudorhotoxane. This is the pictorial representation. If you want to see the real molecules, this is the triphenyl methane molecule, and this is the bipyridine, and this is the cyclodextrin molecule. So this cyclodextrin is in the middle, and these are the bulky groups, or the capping, okay, end capping. So this is end capped by this triphenyl methane, and this is also end capped so that this cannot escape here or here. So you can see this picture. This is the macrocycle in the middle, and this is a dumbbell-shaped molecule. So this is the macrocycle in the middle, and this is the dumbbell-shaped, which is protected at the both ends, so it will not slip. So this is called as supramolecular polygons, or the rhotoxanes. Catenanes is the ring system. You have two molecules. So this is called 2 crossing 2 catenane, because here there is one cross, it is another cross, and two molecules are involved. It's called as 2 crossing 2 catenanes, but here it is 4. 1, 2, 3, 4. So 4 crossing 2 catenane. So these molecules are called catenanes, and there is no covalent or ionic bond. It is just by the help of supramolecular interactions, they have the catenanes, and they perform different supramolecular applications. This is a best example, which is done by Professor Fraser Stoddart. So these two guys, this is one molecule, this is one molecule, they trap each other just like a ring. But you can see there is no covalent bond or ionic bond, right? They are inside. So depending upon the external stimuli, it may be square pyramidal complex or the tetrahedral complex. When it with when it with phenanthrene molecule or with this terphenyl, this molecule, so then it forms the tetrahedral copper 1 complex, or when you change, it forms the square pyramidal copper 2 complexes. It can switch on. So that's what we call it as a switch on of molecular emissions in the case of catenanes. So this is the another one. That's what the second group of scientists, which they have got Nobel Prizes for these molecular missions. So here two macrocycles are encapsulated inside, and this is a bulky group, this is a bulky group, rhotoxane. So when you pass light, it goes like this. When you remove the light, it becomes like this. So it is like a molecular muscles. Okay, biceps, your biceps, it is relaxed and tightened. So this is tightened and this is relaxed. So that they have named as molecular muscles. You have molecular lifts, you have molecular shuttle, you have molecular car. There are many things in the literature you can go and find out if you are really interested in supramolecular chemistry. And apart from that, we have dendrimus. So this is the core. It has three parts. One is the central core, the interior dendritic structures inside, and the exterior surface branches. So this is the core, and you do a coupling. This you get the first generation. Again, you activate at the end and attach the higher coupling. You get the second generation. Like that, we can go. I think so far we have got till G7 or G8 dendritic structures. As a whole, dendrimus, it can have various functions. Okay, so this is dendrimus. Highly branched star-shaped molecules in general. Okay, there are, see, you can see there are many molecules in this. Very, very difficult to synthesis. And then additional, they are called as the supramolecular capsules. So this is one cavitant, 2 times with the help of a guest molecules. The guest molecules, one side it will trap one of the molecule, the other side the other molecules. It becomes as a supramolecular capsules. The same with the help of supramolecular interactions. In the field of nanotechnology, you have fullerenes, which can entrap guests, which is outside is called exohedral. When it is inside, it is called as endohedral. These are also a type of supramolecular molecules, or you can call it as the supramolecular, with the help of supramolecular interactions, these fullerene molecules or the carbon nanotubes, etc. This one is very famous these days, the metal organic frameworks, or sometimes some scientists, Professor Edodi, Professor Omar Yagi, they all call it as metal organic frameworks, but some professor, they call it as metal organic porous materials, because inside they will be porous. This is the construction of frameworks between the metals and the polydentate organic ligands by strong covalent bonds. So this is a macrocycle, and inside these gaps, you can have the storage of hydrogen, methane, or carbon dioxide, all those gas storage. For that, these metal organic frameworks are involved. Nowadays, they are preparing nano materials with the help of metal organic frameworks. And covalent organic frameworks are porous polymer networks. These are all a type of macrocycles wherein the small molecules can reside inside and perform many actions. So far, I'm talking about the supramolecular, all the surface level, whatever there, I've covered up almost all the things. So when you go into the syllabus, it will be an elaborate of all these things. Now you have both. I have a covalent bonding here as well as a hydrogen bonding here. It's the enantioselective selective recognition of amino alcohols and chirality conversion of amino acids, which I did as a little bit of works in when I was doing my postdoc in South Korea. So here you can see the resonant assisted hydrogen bonding is involved. This is what the resonance assisted hydrogen bonding, because after the formation of, this is an aldehyde or a ketone, when it reacts with the amino acid or an amino alcohol, NH2, it forms a skiff base here. And there is a OH here, so that it forms a 6-membered ring. This hydrogen bond, because of this electronegative atom, it forms a 6-membered ring. And this is called as the resonance-assisted hydrogen bonding. And the other terminal, whether it may be OH or COOH, in case of alcohol, it is OH. In case of an acid, COOH, that forms the hydrogen bonding with this side chain. So here involves both covalent and the hydrogen bonding, and it can recognize the chirality involved in amino alcohol and amino acids, besides the steric hindrance here. So this is a chiral receptor, and it involves the covalent bond as well as the hydrogen bonding here, which gives the recognition of whether it is L or D in the case of, or R and S in the case of amino alcohols, or in the case of amino acids. So we have taken this bienol molecule, and we have put a pendant which is attached at here. It is like rotating, because this molecule will be rotating very hard, but once the molecule is formed, it becomes rigid. So to check the effect of this hydrogen, OH, is there a hydrogen resonance assisted hydrogen bonding is there or not, we have protected with CH3. At the same time, further hydrogen bonding is there or not. This aryl group, this is a good hydrogen bond donor as well as hydrogen bond acceptor. To check this, we have acetylated this. This molecule shows good chiral recognition, whereas these two doesn't show. That means this resonance assisted hydrogen bonding is involved, as well as the hydrogen bonding is also involved in this particular case, this receptor. So this receptor, to check that, we have synthesized these two, and this gives good recognition. It forms a covalent bond here. It forms a imine, okay, between these aldehyde and amine. It forms a imine, and then the other end, the COOH or OH will form hydrogen bonding and gives a good chiral recognition. You can see here this uryl group peaks. Okay, these two are the uryl group peak, and this is the imine peak. Once it forms with the alcohol, it forms an amine. It forms an imine. So this NH here, this NH here, that one is this peak, and this one is uryl NH. You can see here, this is what D-alanine, and this is what L-alanine. But when you put DL-alanine, you can see there is a good discrimination. And this is L-binol, okay, S-binol. So because this resonance-assisted hydrogen bonding is there, as well as this hydrogen bonding is also there. So this comes under the supramolecular interaction, and this comes under the covalent interaction. But this resonance hydrogen is also a type of supramolecular interactions. So you can have a good chiral discrimination. But we are very fortunate when we put L-amino acid to this over a period of 2 days. You can see 2 days, there is almost the L. So these are all the uryl peaks, and this is the OH peak. The L goes down, and then the D formation comes up. So totally the L is converted to D. Epimerization takes place. So this receptor is able to, this receptor, binol receptor, when you treat with amino acids, it forms the imine bond here, and the steric repulsion takes place between these two, and the resonance-assisted hydrogen bonding, as well as the hydrogen bonding involved here, it can convert the L-amino acid to D-amino acids in 2 days. So you can see here, this is the evidence with the help of NMR spectra. This is the uryl groups, and this is the imine group. This L imine group at the start of day 0 day, this L, it goes down, and this D comes up. So almost you can see L is down and D is up. So it can give a chiral recognition between L and D, as well as it converts L to D. For serine, alanine, histidine, you can see how this peaks goes down and this peaks comes up over a period of 45 hours. So it's a good receptor for the conversion of L to D, or it can recognize the alcohol L, R, and S separately. Okay. So far, I have given you the basics of supramolecular chemistry. Let me take that into my research, how I am using that for another half an hour, how I am using that for my research purposes. That based on that supramolecular chemistry, I am doing several chemosensor in my laboratory. So for that, based on the fluorescence and UV, naked eye detection, and also based on the fluorescence detection. So everybody know about the luminescence. It's the emission of light by a substance. So when an electron is excited from the ground state to the higher state, from the higher state, when it comes down, it emits the energy as a photon. So that we are working up. Okay, we take that principle. So the molecular excited, that means the outer shell electrons, like in the absorbance phenomena, it will be excited. From when it comes to the ground state, it provides information from where we can do the quantification and qualifications. Previously, the incandescent lights, the incandescent bulbs, these bulbs were used to give lights, but the problem is enormous amount of heat is generated from it. If you touch these type of old bulbs, the heat will be more. So this is not a right way because it produces hot light. But our luminescence is the emission of light at a normal or cool temperature. So depending upon the external stimuli, as I always tell, we have thermoluminescence because you need to excite the molecules. So if you excite the molecule by heat, then they are called as thermoluminescence. If you heat the molecule by electrochemical reactions, then it is electroluminescence. By chemical reactions, it is chemiluminescence. By sound, it is sonoluminescence, so on and so forth. I have listed many of the other, depending upon the external factors, you have the excitation takes place. But we concentrate on photoluminescence or fluorescence and not on the phosphorescence. So we concentrate on fluorescence. The mode of excitation is by fluorescence. The famous Jablonski diagram. So when you excite the molecule from the ground state, it goes to the higher singlet state S1, S2. From there, it comes with radioactive decay and non-radioactive decay. When it comes with radioactive decay, then we call it as the fluorescence. From the singlet ground state to the lower level of the singlet ground state to the singlet state to the ground state. We call it as fluorescence, and it is hardly 10 power minus 9 to 10 power minus seconds. And then you know about the internal conversion or the phosphorescence and intersystem crossing, etc. But you should be advanced. So the modified Jablonski diagram, it includes the thermally activated delayed fluorescence. That means there is a reverse intersystem crossing. So that is, this is intersystem crossing from here to here. But when you heat a little bit, so from here, once again, it goes to this. That is called as the reverse ISE, or it is called as thermally activated delayed fluorescence. That means from this, the electrons again goes here and the fluorescence comes. So this is called as the reverse intersystem crossing or thermally activated delayed fluorescence. This is applied in organic light emitting diodes. So where this fluorescence is used in molecular imaging, as I told, in for targeted drug deliveries and all those things. So you can see here, you put the fluorescence molecules inside. So this may be the cancer cell areas. For a surgeon, it is very easy to identify when you pass a particular particular wavelength of light where it glows. For a surgeon, he can cut off the cancer-oriented places for this. Okay, so you can see here, if this part is cancer-oriented, you can tag that cells with a fluorescence molecule. So there will be, as I told, supramolecular interactions. It is not a covalent interaction. It will tag that molecule there, and when you pass a particular wavelength of light, it will glow, so that the doctor knows here are the cancer cells, so you can do a surgery on that. This is called as the image-guided surgery. For this, 5 persons to be together. One guy is the biologist to find out which are all the cancer cells. The second is the chemist to have a tag the fluorescence molecule to that. The third one is the physicist to have a particular wavelength of light, focus on that to glow, and then a surgeon to do a surgery. And to do this research outcome, we need an investor. So it is an interdisciplinary research. So when all combined together, we come out with this type of technology. That's where we are these days. We have so much of things like laparoscopy, endoscopy, or CT scan, PET scan, MRI scan, everything have evolved like this. So there, the importance of fluorescence is used. And then in diagnosing diseases, the cognitive diseases like Alzheimer's or these Parkinson diseases, this is the normal aging. This amyloid, it is negative, but here it is positive. It will glow and it will tell. So 30% of normal older people are amyloid positive. So they will be having this shivering or forgetting things, which we call the Alzheimer or the Parkinson's diseases, etc. So that can be detected. As I told you, the brain tumor cells, the ovarian cancer cells, you can see this is the indigo cyanin green dye. So that tags with those molecules. So when you pass that light near fluorescence or NIR merge, you can get that glow. So the surgeon can easily do that. So here, indigo cyanin green dye. So this is used for sentinel lymph node tracking. So to track that whether the cancer cells have passed from one place to another. So this is immediately no response. After 4 minutes, after 15 minutes, you can see that glow. So that means there is a cancer cell present in it, in the lymph node, whether it is passed to the other or not, because that is more important. So whether the cancer is spread from head to toe or it is in the particular place, we can use this type of fluorescence. And even in agriculture, for chlorophyll fluorescence imaging for early detection of plant diseases. In the case of Fusarium species, this is 90% infection, you can see here, and here the degree of infection is only 30%, because if it is completely gone, this is only very, very little, depending upon the tagging molecules, which we call it as the chlorophyll fluorescence analysis or chlorophyll fluorescence imaging. Based on the chlorophyll, you find a suitable receptor to hold on to the chlorophyll, and whether the chlorophyll content is good in this plant or not. Based on that, you can tell about its disease. So in agricultural field. And the colorimetric sensor, you can see in the pregnancy kit test. Most of you know this. When you have 2 marks, it's positive. So when a conceived lady, early morning urine, put a drop in this test, you can, if she is conceived, it will show 2 marks. If not, it is negative. Why? Because in this particular kit, it contains chemicals which can capture the gonadotropins, the human chronic gonadotropins, which is released in the urine for a conceived lady early morning. So that will be trapped and will be giving the color. These tests, it's colorimetric tests. Besides the blood sugar test, so the blood sugar test nowadays, you can, besides the glucometer, going to microbiology lab and do the test, you can just have the glucometer test. The main molecule is the boronic acids. This boronic acid captures the sugar molecules with the help of this hydrogen bonding, and it gives you the exact results. So for diabetic patients, you know what are all the readings these days, that is before food and after food and everything. So this guy is responsible for that. So from there only all the other, now there are several others, but the supramolecular chemistry is applications because of hydrogen bonding between these two. Then the ion detection, this is where we are working here. So for different types of ions, for zinc, for copper, you can see here, depending upon the color changes how much amount of copper is present. By naked eye you can see it's 0 ppm, 1 ppm, 2 or 4. Or here, you know, when I show here, it is the iodine test for iodine. These days the thyroid problems are more, so you may know whether iodine, how much, whether it is increased is also a problem, decrease is also a problem. So you can test for this iodine, or you'll be having that goiter problem, okay, the thyroid problems. This is the iodine probe kit test. So like this, heavy metals, for example, silver, cadmium, mercury, etc., for that also this will be used. So my question here is why we are using iodized salt. So in general, if you are less, for example, if you have a deficiency in iron, you can take iron tablets like folic acid or folate, etc. If you are deficiency in calcium, you can take calcium salts, I mean calcium tablets or calcium content. If you are high, they will give certain tablets which will reduce and maintain your body iron content or calcium content. Similarly, the iodine content, you are already hale and healthy, why you want to take this iodized salt? I don't see any salt without iodine in this case in these days in the market. So for the past 10 years, you can see the thyroid problem is also more. So it's left to you to check the answer for that, why we are using the iodized salt. If you are already correct in that level, why do you want to take that? Right. Coming to the drug and chirality, already I have told you how the chiral discrimination done in supramolecular chemistry. So why it is important is, you can see this is R enantiomer, this is S enantiomer in the case of thalidomide. In 1950s to 60s in UK, one guy, this R prevents nausea from vomiting, prevents nausea and vomiting during the pregnancy for women. But this guy is the culprit, this S enantiomer. It forms the cause for the disabled baby deformities, which is called as teratogenicity. So for the 10 years, people were not able to identify this because this is a racemic mixture was given to these pregnant women. And after that, they found out this R enantiomer is good and the S enantiomer is bad. And then the chirality came into picture, and they recognized and they have taken this R enantiomer for good drug, and then they have banned this enantiomer. The approved drugs in the market, 2/3 of the currently selling drugs are chiral, because our body itself is chiral. So much important that chiral discrimination can be done using the supramolecular chemistry. I have shown you an example before, both involving the covalent bond and the hydrogen bonding supramolecular interactions. So these days, recently, the elections, many of you might have voted. So this ink is visible, but sometimes you can just have a mark here, and that will not be visible, but when you pass a certain wavelength of light, it will be visible. So those persons who are cheating, or putting some other ink and taking away, this can be used. Who knows, in future you may use this type of invisible ink for voting also. So there is a greater demand in this era for CT, computerized tomography, magnetic resonance imaging, positron emission topography, plasmogen, activator inhibitor. Everything uses the optical fluorescence imaging. You can see here in hospital and clinical, 30%, and in academics 18%, and in biology 14% they are used. This type of fluorescence microscopy and its studies. So I told about the metal ions in human body: calcium ion, copper, zinc, essential elements, essential trace elements, and their role. Calcium, they strengthen the bones and teeth, and sodium and potassium, they regulate the body metabolism. And if it is disorder, due to deficiency, you have anemia, liver and kidney damage, type 1 and type 2 diabetes, etc., Alzheimer, Wilson diseases, etc. So these are all some of the essential elements. Trace elements, ultra trace elements, the level which needed in our body by determined by the World Health Organization. Their chart is this one: daily allowance of metal ions. And the effect of metal ions, if it is excess, what happens? If it is deficiency, what happens? Effect of silver, you can see neurological diseases, Parkinson's, asthma, bronchitis, cancer, etc. If it is excess of silver, or effect of silver if it is more or less. Effect of aluminum, you may get dementia, lungs problems, kidney problems, acidifying solid, etc. Effect of mercury, in India, the Bhopal gas tragedy, and the Minamata disease in the Minamata Bay in Japan. So still now people are suffering with because of this mercury. What is that? Minimata disease due to the methyl mercury poisoning. Okay, in the district of Harada in 1986. Okay, still people are suffering from this. So these heavy metals, you need to have some sensors. And then the beryllium, lead, thallium, arsenic. These guys are used in these lipsticks and all those things. So this is an arsenic cancer. You have peptic ulcer. For all these things, for kidney damage, skin and lungs and bones damage, you need to have sensors to capture all those things. Because if you go to a microbiology lab for any tests, it takes hours, sometimes days. So you need to have sensors in a day. So what is a sensor? It's a device that measures the physical quantity and converts that into a signal which can be read by an observer or by an instrument. So by nature, we have 5 senses. I need not mention all the natural senses what we have. A chemosensor in particular detects a certain external chemical stimuli in biology and environment and gives you the signals. So this can be constructed. It has a fluorophore, a linker, and an ionophore. This ionophore, this is the major guy which captures the metal ions or whatever guest molecules you are giving. It may be cations, anions, amino acids, pesticides, any other thing. So when it captures, this fluorophore gives a signal. Either it quenches or it enhances or the shifts. So this totally is called as a chemosensor, or you can call it as a fluoroionophore. There are 3 strategies. First strategy, chemosensor, it bears a signaling unit. So when the guest molecule interacts with the host molecules, this fluorophore gives a signal. As I told, it enhances or reduces, or it gives some signal. That is the first method. Second method, this host guests are not effective fluorophores. So you have an indicator. So when this indicator goes, the indicator is displaced from it, it gives the coloration. So this is called as indicator displacement approach. And the third one is called as the chemidesometer. Here there is a reaction between the host and the guest, and then completely the guest molecule. So these two are reversible, and this is an irreversible reaction. Once there is a reaction, it will give some signal, and only once it can be used. It cannot be used again and again. But these guys can be used again and again because they are reversible. I am a bit fast for the want of time. So this is the chemical sensors. So I told you this is the host molecules. There are different guest molecules depending upon the shape and size. Only this guy fits in here. Okay, this should exactly fit here. So it gives some signal that is converted into the signal like that of your whatever the glucometer, etc. So the working mantra here is, if there is no interaction between the host and guest, you do not get any informations. There should be a interactions. So why chemosensor? They give highly selective among the 25 metal. You can have 1 metal selectivity. Among the 22 amino acids, you can have 1 amino acid selectivity. Sensitivity up to nanomolar level or more, picomolar, femtomolar, attomolar, etc. It is rapid. Within seconds and minutes you can have. It gives the chiral discrimination. It is effective, economic, and efficient process. So it can have different applications. In the case of chiral recognition, in recognizing sugars and carbohydrates, in the discrimination of DNA, RNA, etc., explosives, hazardous chemicals, drugs, pesticides, gases, dyes, and pigments in microorganisms. For example, there is different types of gram-negative and gram-positive bacteria. And because of Escherichia coli or Staphylococcus aureus, you get your diseases. But still now, we have to give the culture to the lab, and it takes 3 days to find out what type of disease is it and because of what bacteria. But if you can take the blood immediately, and if you have a sensor, within minutes you can tell this is because of this bacteria you got this disease. But that has not happened so far. So because with the help of these chemosensors and the supramolecular chemistry principles, you can easily discriminate the bacteria and fungal differentiations between the Aeromenes hydrophila, Staphylococcus aureus, or the Escherichia coli. So it would be more advantageous for the humankind. Besides, as I told you, the anions, cations, neutral molecules, pesticides, etc. So you can go through a recent review paper approaches for naphthalene-derived fluorophores and the recognition of aluminum. Okay, so these two my research scholars have done that with different mechanisms, because in the supramolecular chemistry, based on the fluorescence, detection of anions and cations based on the different mechanisms like photo-induced electron transfer, internal charge transfer, excited state intramolecular proton transfer, aggregation induced emission, then you have CN isomerization. There are a lot many concepts that I need another couple of couple of hours to explain. So I'm just telling the mechanisms. Based on that mechanisms, these interactions takes place. So a little bit, another 15 minutes of time. So modular fluorescent organic materials for chemosensing applications. So this is what our design principle. So we have a fluorophore, we have an ionophore, we connected a fluoroionophore. This is enough as a chemosensor. But what we did is we put another fluoroionophore here with the help of a linker. So this total molecule is the fluoroionophore, and this ionophores can capture the cation or anion or the neutral molecules in the middle, so that when you pass light, it can give different signals, either coloration or either enhancement or quenching, or a red shift or a blue shift, what we call the bathochromic or hypsochromic shifts. All those things can be done, can be taken, the signals can be taken. So this is what our molecules. So these are the fluorophores, pyrene molecules, and these are the ionophores, the thiophene molecules, and excuse me, and these are the ion binding sites, and this is the linker or the spacer which links all these things. Now these guys, these heteroatoms, are the binding sites for the metals to be bound. Okay, metals or amino acids, and totally we call it as a modular fluorescent chemosensor, because we can change this pyrene to anthracene, we can change this to phenanthrene, whatever we want. Similarly, this space also, this is aromatic, we can change into aliphatic, we can expand the length of the chain, we can shorten the length of the chain, and we can tune these ion binding sites. So we have several sensors published. So based on this modular xylylene dibromide, we have ortho, meta, and para. This is our trump card. Based on this, change these chemosensors. So this is a sensor for silver, and this is a sensor for silver. But you can see the only difference here is one more additional atom here. There is a nitrogen atom here, but here it is not there. But these two detects with a different mechanisms. And then we have binol here. This detects mercury, and we have anthracene. So we have another binol with a pyrene unit here. This is good for zinc, and we have anthracene here. Now it detects aluminium. So these are all some of the publications from our group over a period of 5 to 6 years. And this is just naphthalene as a molecule, and this is ion recognition, and this is a dual recognition system. It recognizes both nickel and aluminium. Okay, both with different mechanisms. And we have chiral molecule here. We have synthesized this for a chiral recognition, but we have tried even for metals, and this is a good aluminum recognitions. And then we have cerium recognition in the case of quinoline molecule, and this is a strontium recognition. It is still unpublished works. We are underway in that. So let us see one or two, and I will close. So this is the pyrene pyridine conjugate as silver ion selective fluorescent chemosensor. So this is what I told you before. Both are silver sensor. The only difference is here there is additional nitrogen atom. So this is the synthesis. Pyrene aldehyde, all simple synthesis, skiff base, and then a reduction, sodium borohydride reduction. We obtain this compound, and then we treat with metaxylylene dibromide. We obtain this type of modular chemosynthesis. So you can see here only thing is we used 2,6-bis bromomethylpyridine, but here it is just xylylene dibromide. So we introduced this one. So this also silver, this also silver. So you can see here all the metals in fluorescence emission, they are here, but in the case of silver alone, it is quenched. Actually, it is not quenched. So these two are the monomer peaks of this pyrene, but this is the excimer peak. That is, excimer means these pyrene comes together and they form excited dimer. Okay, two pyrene together, so they are called as excited state dimer. So it's called as excimer peak. So the excimer peak is quenched, but the monomer peak is enhanced. That's the mechanism. See, this is enhancing, this is quenching. So this is the mechanism involved here. Excimer enhancement and monomer enhancement and excimer quenching. So where it has the silver sensors. So it is supported with theoretical studies and the mass spectrum 1 plus silver, and also it is supported with the NMR. So NMR data, after the addition of silver, there is a shift in the peaks. Okay, by want of time, I'm not explaining fully. So when you add this nitrogen, when you incorporate the nitrogen here, now what happens? Both the monomer and the emission is quenched. So this guy, we call it as this place is called as the isobestic points in UV, and here you call it as isoemissive point. So this is a ratiometric sensor, so that you can quantify this if you want to use it in real level applications. But here you can see both the monomer is quenched, the hexamer is also quenched because of the additional heteroatom. So one heteroatom makes a major difference. So we were able to synthesize cucurbityril with the help of urea. I did myself for 2 years, but I tried to synthesize thiocucurbityril. Just change the urea molecule into thiourea and tried. Still now, nobody have achieved that. So that one atom, instead of oxygen, if you have sulfur, you cannot have a cucurbityril. So only still now it is cucurbityril with oxygen. There is no cucurbityril with sulfur. It is still a challenging problem. So the one atom makes a major difference in supramolecular chemistry. So that is what this. So you can see it is totally quenching both the monomer peak as well as the hexamer peak is quenching, and some NMR stuff. So where you can have the shift after the addition of silver. And this one is we need to check, because selectivity means in our body all the ions are there. When all the ions are there, our sensor should be particular for only one ion, that is silver. So that is what we do, the interference of other ions. You can see here when all the other ions are existed, but even then our sensor particularly detects silver alone. It will not detect any other ion. If you have a pool of ions in a beaker, and along with that, if you have silver, it will be only detecting silver, but not the other ions. And these are all some kinetic studies, that is the limit of detection and the association constants between the silver and the other molecules, between the host and the guest molecules. And that's what we have given like this as a butterfly shape. Okay, so here it is monomer and hexamer. So why this hexamer? They are close together, but here they are far off because of the silver coordination here. So it is hexamer quenches, but here hexamer enhances. And we did some same images and real sample analysis for the detection of silver in water, tap water and wastewater, and it came out good in this case. So this is the second study where we have introduced a chiral molecule, phenylglycinol. Okay, so phenylglycinol is here, but we call the push and pull mechanism. Here these two guys, the fluorophore, pull each other, but here the ionophore pull each other after the coordination with aluminum. So this is the synthesis, the same simple skiff base and then reduction, and then we use the xylylene dibromate, which I told that's the trump card. You can see here both monomer enhanced and the hexamer is quenched. But when we take this metal, this compound alone, this is also an ionophore, because you have ion coordinating site, a fluorophore, and the linker, everything is there, but it doesn't give any metal selectivity. You can see here, no metal selectivity. But in this case, all the metals are here. Only this one, for aluminum, it is exclusively high. Enhancement is done in astronitrile water medium. So this is particular for aluminum ions. So the other studies, as I told, the IR spectrum and 2D Gaussian, this is the interference studies, and this is what I told you, monomer enhancement and hexamer quenching, and you have a ratiometric, this is the isoemissive point, the ratiometric sensor, which can be used further. And I told you this is reversible. So when you put EDTA, it can capture the aluminum and take away. So you can wash it with EDTA once after the aluminum detection is over. So you can use multiple times. We have tried till 20 cycles. It was good with a little loss of the receptor. So these guys are very much useful for reversible use of detection of aluminum. And we have used that in bioimaging. Okay, so you can see here after the capture of aluminum how it glows. So for any aluminum contamination in your body, we can use these sensors. So that's what we call it as the push-pull mechanism. And then we have changed that to pyrene to anthracene. So this also we have tried to use the captured Escherichia coli alone, in this case the bioimaging, and this is good for aluminum. This is also good for aluminum. So but with a different mechanism, because this is what the synthetic details. And then these are all the NMR and C13 spectra and mass spectra. So this is the interference studies, and you can see it is captures only aluminum. Enhancement for only aluminum besides all the other metal atoms. Okay, so these are all the other kinetic studies and reversibility. And here the pH is more important. You can see here the pH over a wide range of pH, it is almost same, so that you can use this sensor for all the pH conditions from 1 to 14. And also it does the selectivity studies, the studies is completed by 2 minutes. Within 2 minutes, it will sense the aluminum present in it. But we are trying to improve to in a minute or in seconds. Still, the research is going on in our laboratory. So these are all the SEM and EDAX and all those things to supporting data for all things, and then the supporting data for these theoretical studies, right? And this is what the E. coli cells, we have captured the E. coli cells here with aluminum. E. coli cells with aluminum, when we stain, it glows at that particular wavelength. So we are trying hard to do something, some imaging for these type of bacterial cells. Besides, it is used for water studies also. So for want of time, so we have done something recent works. So this is even fingerprinting, latent fingerprinting for silver. And then we have detected certain metals in foods. So we have published in food chemistry, and certain things in water, and then as logic gates, and as in bioimaging. These are all some of our recent publications. Okay, so everywhere so far I have shown everything on the positive side, but it is not the case always. It happens. If you synthesize 10 receptors, only one will be good, 9 will be of waste. Either there will be no selectivity or the molecule will not be stable. So we have planned like this. This is based on the pyrene, and we have nitrogen and oxygen, so we can have a good sensor. This is what our plan. You see what the first step, because of this OH. So finally, this will be a problem when we do this coupling reaction. So what we did is we protected this first. So that is what this protected naphthalene molecule. So that's its NMR. And then we added the aldehyde. So we added this pyrene, and then we got this sodium borohydride. We got this. That is also fine. And then we put the xylene dibromide, because this is blocked by mom. So that xylene dibromide reaction took place here. That is also fine. But finally, the mom should be deprotected for the receptor. But see what happens? The compound is highly unstable. Okay, after all these things, it took us nearly 3 months or 4 months to finish this because of the lack of facilities and all those things. But even then we tried. But finally, after the removal of mom, the NMR is totally gone. That means it is forming some self-assembly. So we are probing some hydrogen bonding, some self-assembly over a period of time. So you don't get any particular spectra. You see here how these spectra are, but see this one. So like this, there are many, many failures. So I have shown you the positive side. There are negative side also. So if these organic molecules are becoming a failure, what next? So blend carbon materials. These days, the nanotechnology. Okay, that's what we do. We took some graphene materials, so that can act as a chemical sensor also. Graphene nanocomposites as fluorescent chemosensors for varied application using the supramolecular chemistry. So we take the graphene molecule, incorporate with organic molecules. So these organic molecules trap the guest molecules, and because of the wide surface area of these graphene molecules, you can have high selectivity and sensitivity for these type of whatever guest molecules you are taking. So these are of some of our publications in materials letters, environmental research, and microchemical actor, etc., for these type of blending molecules. All right, so that also we have in review, functionalized graphene oxide materials for fluorometric sensing of various analytes. A review in materials advances. The scholars, Mr. David, who have recently submitted his thesis, and Dr. Prabhu and Ms. Subna have done this review work. And this is, if you want to have something on fluorescent chemosensor based on this GeoRGO, you can go through this review work. So conclusion, using the supramolecular chemistry principles and following the green chemistry protocols, several efficient and economic chemosensors can be developed for multifarious applications, including water and environmental monitoring, sensing and removing of toxic metal ions, or safety of food, or even in healthcare and chelating drugs as biosensors for iron, copper, magnesium, etc. So what I tell always is watch the society carefully, what your mother does, what your father does, what your brother or sister, what your relatives, uncle, auntie, or what the people does. Watch carefully, catch the problem, what they are suffering from, and apply your knowledge, whatever you have studied, and supply a solution to that without the pollution. Through that way, so much of innovations have happened in our society for the helping the mankind so far. So it is not that what you study, you should always think about that to develop good things. Just see the problems happening in and around you in the society. Still now, I'm struggling to clear a dump yard, what you call in my street. 30 home, we have a dump yard. Still, I want to be clear, but unless the lorry comes and picks up, there is no other alternative to clear the dump yard. So that is a problem. How to clear that? Where is the recycling unit? So like that, think carefully when you watch the society, catch the problems carefully so that you can come with your new solutions. That's the take home message of this lecture. And this is the good drawn picture of Karunya. So this is the famous Bethesda Center, and these are all the main buildings, and we are located here. Our chemistry department is located here in this place, and these are all the girls hostel. Everything is girls hostel. This is the Sirwani main road, and this is the boys hostel located here, and this is the Sirwani Dam, and this is the Western Ghats foothills, and this is called the Sirwani, and always a very pleasant climatic conditions exist here. This is spread of 800 acres, and I need to acknowledge the DST and then Karunya University, our collaborators, and Saif Punjab for the details, NMR and all, and IIT Chennai for mass spectra. And these are all our group members. So these guys, this girl she is in Croatia doing her PhD. This guy is Czechoslovakia, David Dimonte. This is Priscilla, and this guy is doing his PhD in SRM. And this guy, Dr. Bhuvanesh, is in Dubai, and this guy is in Taiwan doing his PhD. This guy is in SRM doing his PhD, and this guy is in China. Recently, from his postdoc, he has moved to a semiconductor industry. I should thank all of them for doing this work. Without them, I would have not presented all these things. Thank you, all of them. And this is my details. And thank you for your listening, and thank you for your opportunities. Hope I am on time, 10:30 to 12. I have finished on time. Thank you for this opportunities. I'm here for getting any comments, queries, suggestions. Excuse me?
Yes, sir.
Yeah.
Thank you,
You
sir,
take some
for
question.
Thank you, sir, for intriguing us with the idea of self-assembly and non-covalent interaction between molecules that have been mimicked from the awe-inspiring nature and natural phenomenon seen in biological macromolecules. Your talk on supramolecular chemistry has kindled the fire in us to know more about the molecules and their unimaginable applications. I'm sure that all of us would remember the mantra, no interaction, no information. Now, this platform is open for queries. Participants are encouraged to post your questions in the chat box. Now, I'm handing over this session to Dr. Uma Maheshwari, Assistant Professor, PG and Research Department of Chemistry, Ethiraj College for Women.
Good morning to all. Students, you can post your queries in the chat box. Yeah, there is a question in the chat box. Dr. T. Sumita Selin, Assistant Professor of Chemistry, Scott Christian College. Ma'am has asked, can catenanes be used for inclusion complexation as that of cyclodextrins?
It's not possible, but because their cavity size is not so much, and between the catenanes, because they are mechanically interlocked, there will be always a disturbance in it. So you cannot have strong inclusion complexes in catenanes.
Okay, sir. Next question is from, can you please explain the energy efficiency and thermodynamic feasibility of self-assembly phenomenon in nature? That question is from Preeta S. from Ethiraj College.
Once again, ma'am. Ma'am, once again, can I have the question, please?
Yes, sir. Can you please explain before post? Can you please explain the energy efficiency and thermodynamic feasibility of self-assembly phenomenon in nature?
Yeah, madam. So nature, it is entropy oriented. Nothing is ordered. It is always disordered. We cannot exactly predict what happens. So it all depends upon the stimuli. What is there, you can have that.
Sir, the next question. Can you please explain the use of these biosensors in the menstrual blood analysis kit used in sexual assault cases?
Okay, so it is in terms of forensic sciences. But these biosensors, they can detect whether the lady is pregnant or not. I'm telling about the positive side. But in these cases, there are several other tests. If there are some sperms is left behind, the spermatozoas, the acrosomes, for those there are certain detectors. So based on that sensors, they can capture.
Thank you, sir. Any other questions from participant side? Sir, no other.
Yeah,
Yeah, there is a question. In MRI, supramolecules are used as T1 or T2.
ma'am,
Yeah,
that
is it?
yeah, that depends, ma'am. Because generally gadolinium complexes are used for MRI scanning. Depends upon the water molecule and which area they are taking.
Okay, sir. Thank you, sir. Participants, yeah. Sir, one more question, sir.
Yes, madam.
What is the length of light you are using for bacteria sensing? That is 133 page of PowerPoint presentation. That is, what
Okay.
are the cells used for bioimaging?
So we are generally using the HeLa cells and using the confocal microscopy, and generally the wavelength will be above 400. It depends upon the fluorophore which you use, and it should be enhancement. Taking bioimaging for quenching is of no use.
Yes, sir. Thank you, sir. Any other questions from the audience participants? Okay, sir. Sir, there is no question from audience side. Shall I move on to the next session, like out of thanks?
Okay, madam. So you can happily share my mobile number or email ID. If there are further queries, they can contact me directly.
Definitely, sir.
Yeah.
Definitely, sir. Thank
Thank you.
you, sir.
Thank you. Thank you.
Yes. On behalf of PG and Research Department of Chemistry of Ethiraj College for Women, I take this opportunity to propose vote of thanks for the national webinar on basics of supramolecular chemistry. First of all, I thank God Almighty for making today's event a resounding success. I would like to express my gratitude to our management, Principal and Head Dr. Mrs. S. Kodai, Head in Charge Mrs. M. Vijaya, and Vice Principal Dr. D. B. Usharani for the continual support and encouragement. It gives me great pleasure to thank Dr. R. Nandakumar, Professor, Department of Applied Chemistry, Karunya Institute of Technology and Science, Coimbatore, for taking time out of his busy schedule for presenting this informative session. So, thank you for sharing your insights into this interesting field of supramolecular chemistry, especially on various applications such as sensors, molecular imaging, drug delivery, and metal extraction, etc. I would also appreciate your time management without excluding any of the significant informations pertaining to the topic. Thank you, sir. I would like to thank my organizing secretary, Dr. G. Goklavani, and also the student representatives, Zalika Mariam, Preetha, and Nasreen of 2nd PG Chemistry for their timely help and support. I also extend my thanks to IQAC coordinator and its members for their constant support. A special thanks to the staff and students of Chemistry Department for their unflinching support and coordination. My heartfelt thanks to the students and faculty members from various colleges for their active participation. I also thank the participants who have registered nationwide and making this event successful. Once again, thank you all.
Thank you, madam. Thank you. Okay, madam, can I leave? Is it all over? Excuse me, madam, can I leave? Is it
Sir,
all over?
yes, sir. We'll end up the session with the college song, sir.
Okay, okay.
1 second, sir.
Yeah, I'm there.
Video file என்ன பண்ணிட்டு கேக்குதான் மேம் இங்க ஒரு தப்பு பண்ணிருக்கேன் மேம் ஷேர் சிஸ்டம் ஆடியோ பண்ணிக்கலாம் ஒரே ஒரு second.
தேடி காணவே முன்வைத்த கால்வின் வாங்கினோம். ஏறுவோம், முன்னேறுவோம். உடல் உழைப்பும் உள்ள பறிவும் ஓங்கும் செல்வ நிதியமும் மழை திறந்த வெள்ளம் போல மனமு வந்து நல்கினார். அழுதையக்கும் கல்வி கோயில் வாழ்வுடனே நிருப்பேன். மொழை மழலாம் எத்திராஜன் கொள்கை வழி செல்வோம். ஏறுவோம், முன்னேறுவோம். பாட்டுடனே அறிவியலும் பலகலையும் பயிலுவோம். நாட்டினிலே அறத்தை காக்க நல்லொழுக்கம் பூணுவோம். ஏட்டினிலே கற்ற கல்வி என்றும் எங்கள் நெஞ்சினில் கூட்டும் தெய்வ பக்தியோடு தேச பக்தி ஓங்கவே. ஏறுவோம், முன்னேறுவோம். வயது தெய்வ தீபமாக ஒளிரும் கல்வி சுடரினை முயன்று தேடி காணவே முன்வைத்த காற்றின் வாங்கினோம். முயன்று தேடி காணவே முன்வைத்த காற்றின் வாங்கினோம். முயன்று தேடி காணவே முன்வைத்த காற்றின் வாங்கினோம். ஏறுவோம், முன்னேறுவோம், என்றுமே முன்னேறுவோம். எங்கள் எதிராஜ் கல்லூரி ஏற்றப்பாடு தேடுவோம். ஏறுவோம், ஏறுவோம், முன்னேறுவோம், முன்னேறுவோம். ஏறுவோம், ஏறுவோம், முன்னேறுவோம், முன்னேறுவோம். ஏறுவோம், ஏறுவோம், முன்னேறுவோம், முன்னேறுவோம். ஏறுவோம், ஏறுவோம், முன்னேறுவோம், முன்னேறுவோம்.
Thank you, sir. Thanks for joining, sir.
Thank you, madam. Thank you so much for the opportunity
Very
provided.
nice session, sir. Very interactive,
you,
very
madam.
nice session, sir. Thank you, sir. Good presentation, sir. Thank you, sir.
Thank you, madam. Thank you. Thank you so much.
Thank you, sir.
Thank you.
Thank you.
Yeah.
Participants, feedback link will be posted now in the live chat. You are requested to fill the same to get your e-certificate. 1 second.